Let's look at section 4.2, and it starts out, there's a couple of theorems that we need to look at. And again, it's not important to me that you totally memorize the theorem, but rather that we understand it. All right, Rolle's theorem says that suppose y equals f of x is continuous, so that's important. Whoops, don't want blue. Is continuous at every point in the closed interval AB, and it's differentiable at every point of the interior. If f of A equals f of B, then there's at least one number C in between there at which the derivative f prime of that number is equal to 0. Now, what does that look like visually? All right. Says that a differentiable curve has at least one horizontal tangent between any 2 points where it crosses a horizontal line. So here's f of x. Here's this horizontal line, and it's saying here's your A value, here's your B value, here's f of B, here's f of A. That somewhere between f of A and f of B, there is a horizontal tangent, and a horizontal tangent means f prime is equal to 0, okay? And the conditions had to be, remember, f of A had to equal f of B. Well, that is because this horizontal line right there. And so here's that horizontal tangent. Now, there could be just one of those, or it might have more than one. So right here, we've got f of A is equal to that, and f of B is there. So there's my horizontal line that the curve goes through. But what happens? We've got a tangent there, here, and 3 different places where f prime of C is equal to 0. So that's what Rolle's theorem says, okay? There could be no horizontal tangent if the hypotheses don't hold. So what's wrong here? Between f of A and f of B, it's discontinuous at this end point, okay? We got an open circle there. On this one, it's discontinuous at an interior point between A and B. Right here, it's discontinuous. And this one, it's continuous at A and B, but not differentiable on an interior point. When you have a cusp like that, it's not differentiable there. Okay? So when you look at that main definition, there were several conditions that had to be holding. Okay, so you might want to go over that. The mean value theorem says suppose y is equal to f of x and that it's continuous. Okay, it's continuous, closed interval, and differentiable. Then there's at least one point C in between those points at which f of B minus f of A over B minus A is equal to f prime of C. And this part should look fairly familiar. That's like the average change. So at some point, it's saying there's at least a point C where the average rate of change is going to equal the instantaneous rate of change, which is what this is. That's the instantaneous rate of change at C, and this is the average rate, okay? So that's what that is saying. And geometrically, there's a little picture here that's saying between A and B, there's at least one tangent that's parallel to this chord AB that's drawn when you connect f of A and f of B, that you get this tangent that's parallel. All right, so let's look at the problems. We don't have too many. I think there's 7 in here. All right, and there's a little tactics to work through these. Find the value or values of C that satisfy, and there we go, there's the mean value theorem that's stated right there, okay, for the following function and interval. So every time you get something like that, they're going to give you a function, and then they're also going to give you a particular interval. All right. So what you want to do is find f of A and f of B. So that's what's done over here, f of -1, and that means, of course, just plugging it in. and we got 0, and f of negative 3 is 36. So it's 0 minus 36 over b minus a, so that's negative 1 minus a negative 3, so we have 2. So we get negative 18. So this part is equal to negative 18. And then f prime of c. Okay, f prime of c. We don't really know what c is, but let's take the derivative of this guy. So if we took the derivative of that, we would have 10x plus 2. All right, so instead of x, I'm substituting c, because this is f prime of c. So 10c plus 2 has to equal this, because here's the f of b. We just found that. So you take the derivative, substituting c for x, set it equal to the value you found here, and solve for c. Because that's what it was asking us to do, find the value of c. All right, so it's not too bad. Number 2, same thing. We've got a function, and we've got an interval. So I did f of 9, and so you get square root of 5. F of 4, you get 0. So we have square root of 5 minus 0 over 9 minus 4. So that's square root of 5 over 5. So this is that value that's going on one side of the equation. F prime of x, remember that you would want to rewrite that if you were taking the derivative. And it would be x minus 4 to the 1/2. Okay, and so when you take the derivative, you get 1/2 of that to the negative 1/2. And so you have 1 over 2, and then this is the square root that goes on the bottom. So I've written that. That equals that value we found. And it's real easy this way to just do a cross multiplying, which is what I did. 5 times 1 is 5 equals 2 times. Now, if you've got the square root of c minus 4 times the square root of 5, that can become the square root of 5c minus 20. You can multiply under the radical. So that's what happened here. Then I divided by 2, okay, because we're solving for c. Then I took this, then I squared both sides. All right, so you get 25 over 4 equals what's inside. Add 20 to the other side. Now, where did I get this 105? Think about it. 25 over 4. If I'm adding 20 to the other side, it needs to have a denominator of 4. So that would be plus 80 over 4. And that gives me 105 over 4. Okay? Equals the 5c. Divide by 5. You get 105 over 20. You can reduce that to 21 over 4. And that is your value of c for that question. Okay. All right, same way with this one. Again, we have, here's my function, and here's my interval. And so f of 10 is ln of 10 minus 5, so that's ln 5. And that's ln of 1, so I have ln 5 minus ln 1 over 4. Okay? F prime of that, remember the derivative of ln u is 1 over u times u prime. Well, u, the derivative of that would just be 1, so it doesn't affect us. So we've got 1 over x minus 5. Substitute your c, and you've got this. So if I do that same cross multiplying, I've got 4 on one side, then I've got c minus 5 times ln 5 minus ln 1. Okay? Okay, so then I'm solving for c, so I'll divide both sides by this. Okay, so that's getting divided on the other side. And then ln of 1, you're at that point, and then I added the 5 over. So now you're doing some evaluating if you can, and ln of 1 is 0. That's something we pretty much should remember. And then you can leave this in this form, 4 over ln 5 plus 5. Okay, and the plus 5 is not on the bottom, it's just out to the side. Okay. Number 4. We're kind of doing some evaluation of our theorems here. Show that this function has exactly 1, 0 in the interval -1 to 0. So what theorem could be used to do that? The intermediate value theorem. Okay, that's one that we should kind of remember. To apply it, you want to evaluate at each endpoint, and you're looking to see if there's a change in sign. So f of -1 is -3, f of 0 is +3. Since there was a sign change, we know there's at least one solution or 0 in there. This would be a pull-down menu, and at least 1, 0 would be one of the choices. All right, now it says, now determine whether there could be more than 1, 0. Well, Rolle's theorem, remember, says the deal about f of a equaling f of b. All right, and it's got to be that f prime of c would equal to 0 too. One number in c that would get that. Well, let's look at this. Take the derivative of that and you get 4x cubed plus 7. So that would go in that box. Can the derivative be equal to 0 in this interval? Well, if you solved that for 0, you would get something like that. And so x would be the cube root of -7/4. And you can take the cube root of that, but it's like -1.2 something. I think, if I remember correctly, when I did it. So that's not in that interval. So that derivative can't equal 0 in there. And so that's what you're kind of trying to see. Is there a number c in there at which the derivative could equal 0? And there can't, so that's a no. According to Rolle's theorem, can there be another one? No, since we can't get f of a equal to f of b equal to 0, since we don't have that, we know there's only going to be one number. So those two would both be a no. All right? All right. Number 5 and 6 make us think a little bit differently than we've been thinking, and it's getting us ready for chapter 5. Given the velocity v equals ds dt, so that's the derivative of the position. Remember, position is usually s is the position function. Okay? And the initial, let's see, find the body's position at time t. Okay. So it's wanting us to go from knowing the velocity to knowing the position. For those of you that have had calculus before, you would know how to do that already, but we don't, and so we're not going to go there yet. That'll happen in chapter 5, but we can think through this. All right, so if the velocity is equal to ds dt equals 9.8t plus 13, we're trying to think of a function that if we took the derivative of it, we would get 9.8t. Well, remember, when you take the derivative, to get t, you would have had to have started with a t squared. And you would have multiplied that 2 by something to get 9.8. So if you divide 9.8 by 2, you get 4.9. So 4.9 t squared plus, and if the derivative is a constant, go up one, it would be 13t. And plus, you'll have some constant at the end. So that's what they're asking us to do, is kind of think backwards on that. All right, now, it says s of 0 equals 20. We're going to have to use that to figure out what that c value is. If s of 0 equals 20, okay, that means you're going to plug in 0 for t. So you would get, what do you get? Whoops. You would have c equals s of 0. And s of 0 is 20. So 20 equals c in this particular instance. We plugged in 0 there for time, and we end up with c equals s of 0. But here we were given s of 0 is 20. So here's your equation. Now, a way to check that. Remember, this was what we were given for the derivative. If this is our original position, take the derivative of that. 2 times that is 9.8 t, you would drop down one level, plus 13. And you didn't have that constant there. Okay? So that's what they're looking for your answer. That's going to go in the box there. Let's kind of do the same thing here. Find the position given that acceleration is 18e to the 3t. So acceleration is the second derivative. And they do give you a couple of things. They give you that v of 0 is 20 and s of 0 is 5. All right. For us to go up one level, when you're talking about e to something, like the derivative of e to the 3t is e to the 3t times 3, right? Okay, so we have to think of something that if I multiplied it by 3, I would get this. So divide 18 by 3, you get 6. 6e to the 3t plus some constant which we don't know. And let's check ourselves. What's the derivative of this? It is 6e to the 3t times 3, which would give me this. Okay? All right, at time t equals 0, v of 0 equals 20. So if I plug in v of 0, I let time be 0 in my velocity equation, I've got 6e to the 0 plus c. E to the 0 is 1. So 20, which I plugged in from right here, v of 0 is 20. So 20 equals 6 plus c. That must mean that c is 14. That's the constant that will end up going there. Okay? All right, so now I have that. ds dt is 6e to the 3t plus 14. Now find a function, because we're at the velocity. We got to go up to the position. Now find a function with a derivative that is equal to that. So, again, what did we do up there with the 18? We divided by 3. So we're still with the 3t. We got to divide by 3 again. So we get 2e to the 3t plus, this will have had to have been 14t plus some constant. All right, at time t equals 0, we know that s of 0 is 5. That was given. That's given to us. All right, so s of 0 equals 2e to the 0 plus 14 times 0 plus c. So s of 0 was 5. 5 equals 2 plus c, so c must be 3. So our position function would be this right here, 2e to the 3t plus 14t plus 3. And there we go. That's our position function. So what you're really having to do is think about getting from a derivative up one level and thinking about, well, what did I have to do to get down? So it's really a thinking process. All right, last one. On a certain planet's moon, the acceleration due to gravity is 2.5 meters per second squared. If a rock is dropped into a crevice, how fast will it be going just before it hits bottom 27 seconds later? All right, so acceleration is the derivative of the velocity. All right, and so we know that acceleration is 2.5. So if we were going up one level, we would have to add the variable. So velocity is 2.5t plus c. Now, c is 0. Okay, let's think about that. Because, let me write this down here. Because the rock is initially at rest, right? V of 0 has to be 0. And if you substitute that for v of t, if I could write a b, we'd be good. Substitute 0 for v of 0 and, not v of 0, for v of t and for t. Okay, so if I do that, I get that 0 equals 2.5 times 0. So 0 is 0 plus c. So c has to be 0 in our equation. All right, so it's negligible. When t is 27, go ahead and plug your 27 in there, multiply it by 2.5, and you get 67.5, because that's what we're asked to find. All right, so I think that will get you going on 4.2.